Hello, welcome to my talk on solutions of Navier-Stokes equation, the Hagen-Poiseuille flow. Hagen-Poiseuille flow is a laminar pipe flow for which we have the analytic solution for such a flow. In this talk, I will introduce the fluid dynamics equation and how we can solve the fluid dynamic equation for a special case, the laminar pipe flow. And then I will introduce the Hagen-Poiseuille flow, the laminar pipe flow. And then I will make the problem analysis and the relevant equation simplifications. And then we will solve the equation. And finally, we have a discussion on the pipe flow, the laminar and the turbulent flows. For fluid dynamics, Navier-Stokes equation is the universe governing equation. Here, we look at the problem of incompressible flows. For such flows, the continuity equation would be given as this. And we have also the momentum equations on x direction, on y direction, and on z direction for the velocity component u, v, and w. This Navier-Stokes equation is a complete fluid dynamic equation. Here, we have four equations, and there are four unknowns: the velocity component u, v, w, and the fluid pressure P. For a correct solution to the fluid dynamics, the solution must satisfy the equations and the relevant initial and boundary conditions. Here are the example Hagen-Poiseuille flow. This is a laminar flow in a long horizontal circular pipe of radius r. The pipe flow is under a constant pressure gradient, delta P over delta X. Our target is find the fluid velocity distribution in the pipe. To produce such a flow in x direction, we need a higher pressure at the left-hand side and a lower pressure at the right-hand side. Therefore, we have a normal pressure gradient. Delta P over delta X is smaller than 0. This is in contrast to the more difficult problem, the reverse pressure gradient, where delta P over delta X is larger than 0. This means a higher pressure at the right-hand side of the pipe. The pressure is against the flow. Now in this slide, we first analyze the problem. So from this, we can see under the pressure gradient, a laminar flow can be imagined as seen in this picture. However, the exact form of the velocity distribution would be determined when the solution is obtained. As such, the velocity component would be v and w are both 0. That means that velocity on y and z directions would be 0, meaning there is no radial flows in the pipe unless the flow becomes turbulent. The velocity component u should be independent of x, since here we consider a steady flow. Thus, the velocity component u would be the function of y and z. The flow is asymmetric in the pipe. So for the flow, the dynamic equation would be the moment equation given as this. We have seen this from the Navier-Stokes equation, as well as the flow must satisfy the continuity equation, the simple equation here. To solve the Navier-Stokes equation, we need consider the initial and the boundary conditions. Since here we consider a steady flow, hence the initial condition is not needed. And for the boundary condition, it would be no slip condition on the pipe wall because the flow is viscous. Now we look at the Navier-Stokes equation, the moment equations, and consider the velocity component as we have shown before. Therefore, we can see this local acceleration is 0, and the partial differentiation u with regard to x would be 0. Vw would be both 0, and this term would be 0. Therefore, the moment equation for u would be reduced as this. And for the moment equation for v, we can see all these terms would be 0. So the simplified moment equation would be given as this simple one. And for the moment equation for w, all these terms would be 0. Thus, the moment equation would be reduced as this. And for the continuity equation, we can see all three terms would be 0. Therefore, if the velocity given in this form, the continuity equation would be satisfied automatically. So, in solving the dynamic equation for this example, the continuity equation is not the target since it is surely satisfied. For the Hagen-Poiseuille flow, the pressure gradient would be a constant. And we look at the simplified moment equations. This one is the equation to be solved. And from this simplified moment equation, we can see the fluid pressure is independent of y. And from this simplified moment equation, we can solve the pressure given as this. Here, the pressure is understood to be the function of x and z. And we can solve the pressure from this equation as this. And the function P1x would be decided by consider the constant pressure gradient delta P over delta x, since the partial differentiation of pressure with regard to x would be same as the delta P over delta x. Therefore, we can solve P1x given as this. Here, P0 is the reference pressure at x and z are both 0. Thus, the full pressure expression would be given as this for the Hagen-Poiseuille flow. And if we calculate the partial differentiation of the pressure with regard to x, we can see it would be independent of z. In fact, it is a constant, as we mentioned before. Now we look at the problem. Although the pressure in the pipe would be dependent on that in the vertical direction, but this part of the pressure minus rho gz would have no influence on the fluid velocity component u from this equation. And for a practical purpose, the pipe is a very long pipe. Its length is much larger than its diameter. So the pressure change in z direction minus rho gz would be small when compared to the pressure change along the pipe at the x direction. Hence, in most cases, the part minus rho gz in the pressure expression is generally ignored, as we see in most textbooks. As we have mentioned before, the flow in the pipe would be asymmetric. Thus, it can be treated as a 2D flow. So, we can solve the 2D problem in a simplified manner. See the plot here. Now, for the 2D problem, the velocity component u would be the function of y only. We use y here. Sure, we can also use z or any other variables, but the result would be all same. For the 2D problem, the simplified momentum equation would be further simplified, given as this. This is equivalent as this. Here, the partial differentiation of u with regard to y is replaced by the normal second-order differentiation of u with regard to y, given as this. And this differential equation can be easily solved. The general solution of the velocity component u would be given as this. Here, C1 and C2 are the constant, which can be decided by applying the boundary conditions. Now, we apply the boundary condition at y equaling to r here and y equaling to minus r here, and the non-slip boundary conditions are applied at the pipe wall. So this would be 0, and from the general solution for u, we can obtain C1 equaling to 0, C2 equaling to this value. And we would have an expression for the velocity distribution u given as this. This is the solution of the velocity distribution. And we can see the velocity distribution would be parabolic. We can see here, we put the minus delta p over delta x as the value since it is positive in this case. Otherwise, the flow would be in an opposite direction. And obviously, we can see the maximum velocity would be at the center when y equaling to 0. So the maximum velocity would be given as this here. Now we may have a question about the solution. Is this solution correct and unique? Since in solving the dynamic equation, we assume the velocity, for instance, v and w are 0, and u would be the function of y only. See this 2D problem. The answer for this is because when the solution satisfies the dynamic equation, while the relevant boundary conditions are satisfied, then the solution would be correct and unique. Now we can calculate the volume flow rate through the pipe. Look at the vertical section of the pipe. It would give something like this. And the velocity distribution would write as this. Here we use r instead of y because of the flow distribution would be asymmetric. Hence, the flow rate would be calculated as the velocity times the area, like this ring area, and the integration from the center of the circle to the pipe wall r. and substitute the velocity into the integration, we have the expression as this. And the integration would be easy given as this and this. We can calculate the average velocity of the flow U bar given as the flow rate divided by the area of the pipe, pi r squared. So the average velocity would be given as this, and we can see it is half of the maximum velocity at the center of the pipe. So from this relation, we can see in the laminar flow, the Hagen-Poiseuille flow, the pressure drop delta P would be proportional to the average velocity U bar. And the average flow velocity is half of the maximum velocity U bar, equaling to half U max. Now in this slide, we will look at the pipe flow, the laminar flow, and the turbulent flow. For laminar flow, the condition would be given as the Reynolds number Re is less than 2,300 based on the reference. And the turbulent flow would be given as the Reynolds number is larger than 4,000. And in between these two Reynolds number, it is the flow transition from laminar to turbulent. These Reynolds numbers would be slightly different from the Reynolds experiment. He gave the result for the laminar flow when Reynolds number is less than 1,900, and the turbulent flow would be when Reynolds number is larger than 2,000. Yes, we can see the difference here for the accepted values now. Although looks like a huge difference, in reality this is still very small. We will see this later. And if we look at the fluid distribution, we can see for laminar flow, the profile of the velocity distribution would be parabolic, as we have shown in the previous slide. While for the turbulent flow, it would be given something like this. In fact, this profile is the averaged profile. In reality, the turbulent flow, the velocity distribution would be something like this. Therefore, for the pipe flow, we might have a question how we can express the velocity. In laminar flow, we can use U max to represent the pipe flow velocity, since U max is a well-defined value. But for the turbulent flow, the variation is very time-dependent, and the U max would happen in different places. So U max is not a good number for the turbulent flow. Instead, we are often to use the average velocity U bar for the flow in the pipe. See this average velocity for the flow. As we have obtained in the previous slide, U bar would be half of U max. And for turbulent flow, average velocity is a better physical parameter to indicate the flow velocity. And one other reason for the average velocity is the flow rate can be simply calculated as the average velocity times the area of the pipe. This calculation can be correct for both laminar flow and turbulent flow. So in the last slide, I've given you some value for the flow of the laminar flow and the turbulent flow. Now take a pipe of a diameter 0.1 meter as an example. So to maintain the laminar flow, the average velocity would be given as U bar smaller than 2,300 divided by this value. So the velocity would be very small, 0.023 meters per second. This is a very small speed of the flow. And if we reduce the pipe diameter, the velocity would be increased, so we can still maintain a laminar flow. For instance, if D1 equaling to 0.01 meter, so this is about the size of our sun, or many pipes in the water supply in our house. So U1 bar would be given as this, and the velocity would be 0.23 meter per second. Again, very small flow velocity. For such a flow, we need more than 55 seconds to get the 1 liter water, or 1 kg of the water. Or we need about half a minute to get a cup of water, a large cup. So, from this example, we can see the practical flows are mostly turbulent. Since to get the laminar flow, the flow velocity would be too small to be practical.